cloud. Okay, so for me, it just said recording in progress. So now you all know that that is happening, and you'll need to say yes if I've done this correctly to being here in the recording. For those of you who are curious about the recording later on, once it processes, usually in a day or two, I post it to starhop.com, to our website on the blog. And so you'll be able to find it there, but you can always reach out to me and I can send you the link to the recording as well. So thank you all for being here on our first Friday of August for another Superstellar Friday virtually. And at this point, we've been doing it now for like 15 months. So I feel like some of the stuff we figured out and some of these pieces we're still figuring out. But I know everyone's looking forward to eventually maybe seeing people in person again. And I think that would be very exciting. But for the moment, this is a wonderful way for us to learn something new, get information from people in all different STEM fields, and also even do this from the Bahamas, which I find wonderful right now. My name is Mirka Zaplatel, and I'm the Director of Education at the McAuliffe-Shepard Discovery Center. And tonight I am very excited because we have something that does take us back to the sky and looking at the stars, but in a way that probably some of us have never done in terms of looking at those stars and thinking about how we navigate. So we are so lucky to have one of UNH's docents with the Sea Grant program, Nate Hazen, here to talk to us about celestial navigation. And he has already been very clear that this is not going to be the kind of thing where in 45 minutes we can all go get in a boat and figure out what we're doing. But it'll be a great introduction to all of that. And for those of us who are now have our interest peaked, he'll also provide some information and to get us kind of thinking about it. And then we can always go and learn some more. So I want to thank Nate for being here. I'm very excited about this program, and I want to thank everyone else who's here. The way that we'll do this is I'm going to turn it over to Nate in a moment. The chat will always be open, and the Q&A will also always be open. So if you have questions or comments or something like that, you can always post them there. Remember that if you use the Q&A option, other people can see your question. And that means that if they have the same question, they can vote for it. So you can kind of vote up a question if there's one that's really big for you. And that kind of sends it to the top of the list. And so I'll be monitoring that stuff. Nate will be giving his presentation, and then anything that shows up in the chat or the Q&A, I will feed to him. Okay. So Nate, thank you so much for being here. I'm going to mute myself and let you take over.
Fine, Mirka, thank you very much. And I'm going to share a screen right from the beginning. Then we'll try to zip through this fairly rapidly. It's going to be 101, Celestial Navigation 101, the beginning of a subject. So let's do that. I'm going to share the screen right now. And here it is right here. And then we'll go to a whole screen, which is down here. Let's see whether that works okay. Here we go. Okay, so we're all set. So I'm pleased to talk to you all. I've been teaching celestial navigation in one form or another for many years, and I've always been intrigued by this picture by Winslow Homer. First off, it's a delightful image of a captain and his mate. Captain taking sights and the mate recording the data. And its name is 8 Bells, and we'll find out why it's called 8 Bells in just a moment. And I'm very pleased to be presenting to the McAuliffe-Shepard Discovery Center tonight. So I'll spoiler alert to begin with. This will not fulfill your wish to become adept at celestial navigation, because there are lots of little minutiae and details that we will not be talking about. But we want to talk about the big concepts, and that's what we'll be doing. And it'll be an overview, understanding the steps that constitute the practice. We'll also have to learn some nomenclature as we go along. Sorry about that, but that's what you have to do in any new technology. And it's my belief that you can understand these basic concepts that we'll be talking about and be ready to move ahead in later time if you're so inclined. So let's start here and talk about Earth coordinates, how you measure where you are on the Earth. The standard way to do that for 500 years or longer is with latitude and longitude. And latitude is this number right here, as you can see, which is an angle measured from the center of the Earth. It's the amount you're north or south of the equator. And longitude, which is right here, is the amount you are either east or west of the prime meridian in Greenwich. That was decided in the 1880s in an international conference that longitude will always be measured from Greenwich, and it has been ever since, 140 years. And all those angles are measured as from the center of the Earth. See if I can make my arrow go here. Right there's the center of the Earth right there. So for many hundreds of years, maybe even thousands of years, navigators have used the observation of the sun at local noon, or perhaps the evening side of Polaris, to establish their latitude, how far north or south they are of the equator. But longitude has always been a problem until relatively recently, meaning 150 years. Accurate time was not available generally, and change in longitude, and longitude was a matter of estimation. You sort of guessed how much easting and how much westing you were doing in a given period of time, the change in longitude. At the end of each watch, a captain or a mate would inspect the transit board, and we'll see a transit board in just a moment, and make a best guess of the amount of easting or westing that was done in that 4-hour period, that watch. So let's talk about the noon sight first. The sun rises in the east, reaches a peak altitude about in local noon, and then sinks into the west. And by observing that peak altitude and combining it with the sun's declination, we'll talk about declination in just a moment, it's the sun's latitude, not your latitude, but the sun's latitude. And you can combine those two and find out what your latitude is right here by taking the altitude that you measure with your sextant and taking it away from 90 degrees and adding it to the sun's declination. And back in the day, the sun would observe the sun's peak altitude. He would declare when he observed that peak altitude and had it recorded, he would say, make it noon, because who knows where the ship was, but the ship's time would start anew at 8 bells, and 8 bells will be struck, and ship's day would start right there on board. So here's a transit board. Here's an old one right here. There's a series of 8 holes and every series of azimuths. In this particular, every half hour, the mate on the watch would put a pin in to show what direction, in best guess, was being transited in that half hour. And you'll notice this, and there are 8 holes. And at the end of the watch, they look at all these things. As we can see here, you can say, by and large, on that watch, we are going northeast or east-northeast, by and large. And down at the bottom was where they're keeping track of the ship's speed every hour. And they would take that combined and with a 30-minute sandglass, which was by the helm. And every time the sandglass was inverted, the bell was struck. And every 30 minutes, a bell would be struck, and did that 8 times. That's the end of the watch. And the mate would look at this and make a guess of what was the average distance direction they went and the average speed they went, and build that into the plotting of the ship's progress on a chart. So all of that changed with the creation of accurate seagoing timepieces. John Harrison produced the first successful chronometer in the late 18th century, and they've been developed ever since and were in active use in navies and merchant marines all the way up through the 1960s or 1970s. Here's a classic chronometer. That happens to be an American chronometer, but Hamilton actually. For accurate celestial navigation, it's necessary to know the time to within a few seconds of time if you want to place yourself in the world within a fraction of a mile, a few seconds of time. Interestingly enough, the modern GPS now has extremely precise timekeeping. It's as accurate, more accurate than any reasonable chronometer, but we'll come on to that in a little while. So with accurate time, starting in 1780, and with an almanac, which was a collection of predictions of where the celestial bodies might be, the geographic positions, you can look up with the accurate time, you can look up the geographic position of those bodies anytime you want, for every date, every hour, every minute, and every second for the whole year. And these almanacs are published annually. They've been published that way for over 100 years, 120 years. So let's talk about what geographic position is. Geographic position is the place directly under some given body, in this case a star, as a line from it passes to the center of the Earth. Where it intersects the Earth's surface is called its geographic position. That's a new term. And those coordinates are known precisely and tabulated in the Nautical Almanac to a small fraction of a mile and to the nearest second. And its location, as shown in this lower right diagram, are measured in different coordinates, but the Greenwich hour angle is the position, how far east or west of the Greenwich meridian is, and it's the equivalent of the longitude of the geographic position. And the declination angle is how far north or south. I gotta figure out what this works now. How far north or south of the equator it is. So here's the geographic position, and that's the equivalent of latitude. So a geographic position has a longitude, which is called Greenwich hour angle, and a declination angle, which is the equivalent of its latitude. But that is not a stationary position, because as the Earth rotates, it's moving westward at 15 degrees an hour. And the almanac keeps track of all that. So a typical daily page will look like this. This happens to be May 6th, 7th, and 8th of the year 2016. On this side, the position of the 4 planets, the navigational planets, and the 56 navigational stars. And on this side, the positions of the sun and the moon, along with other data that have to do with twilight times. So these are, the daily page shows the hourly positions, and then we go into a table in the back of the almanac to get the increments to minutes and seconds of time. So let's move ahead to talk about the means by which we measure altitudes. We do that with a sextant. And it's the iconic image of the subject of celestial navigation. Of course, there's a picture of one right there, a fairly recent one. Here's a picture of somebody holding it, making an observation of the sun. Daylight, notice. In fact, the sextant's only a minor player. The sight reduction can be largely done without having taken a sight with it, as we'll see in just a minute. And we typically, as a beginning navigator, we navigate principally with the sun because it's available 8 or 10 or 12 hours a day, every day of the year, except when it's cloudy, as contrasted with the planets and the stars, which are only available for a 45-minute period in dusk and in evening twilight. So let's look at this and do an animation of this, look at making the observation. You notice we're swinging the sextant's limb out, and now we swing the sextant back and forth and kiss it to the horizon. Let's do that again. So we unclamp it and we swing out the index arm, bring the sun down to the horizon, adjust and tilt the sextant, make sure where it's dead vertical, and then make the observation. So here's the process in a different view. We bring the body down close to the horizon, in this case, the sun, and we'll be talking mostly about navigating with the sun, in fact, entirely today. We'll call out ready to our recorder. Typically, you will be taking an observation yourself and have a recorder alongside of you to record the sextant reading and the time. Swing the arc to see whether it's vertical. The sextant is vertical. Final adjust to kiss just touch the horizon. Call out mark, and then the recorder will record the exact time to the nearest second and record the sextant reading that you will read. Now let's see how we do that in just a minute, not the time, but let's see how we do the sextant reading. So here is a sextant in which a observation has been made in the fall, probably, in the altitude. You'll notice there's an index mark here, and there's a drum, which if you rotate this drum one revolution, that index mark will move just one division. These are every single division. So 29 degrees, 30 degrees, 31 degrees. So we look at both the limb and the drum and decide whether it's small minutes or large minutes. I say that right now because this number, this arrow is showing not quite 30, but much higher than 29. And we can see that right here too, because this 0 is at 42.5. That's large minutes. So that confirms that we're pushing up on 30, but not beyond it. We combine those carefully. So this reading, if I were to read it, would be 29 degrees, 41 to 42 minutes and a half. And that's it. Call out to your recorder. 29 degrees, 42.5 minutes, sir. Some of the things you might observe are a star, although we'll not be talking about that. And that's typically a point source, so you'll bring it right to the horizon. The sun, in this case, what we call the lower limb of the sun, to touch the horizon. When it's really cloudy, you might try this and bring the center of that smudgy image of the sun so it intersects the horizon, but that's typically pretty bad sight. On the moon, here we might use the lower limb of a gibbous moon or the upper limb of a crescent moon. So those are all different observations that you might make, and they're all involved bringing the body down and having it touch the horizon in one way or another. So the sextant's measurement is of the body's altitude, and we call it H. H is the term for altitude among navigators, capital H. And what we just observed, O, observed, after a few corrections, is called H sub O, observed. And then the sight reduction process, which we will do, and I will describe that in just a moment, determines what the expected altitude should have been at that time. We can do that site reduction process without ever having made an observation. If we want to say what should the expected altitude be at a certain time, we can do that calculation without ever having made an observation. But that site reduction, that calculation yields an altitude called H sub C. So we have H sub O and H sub C. The difference between the two, H sub C minus H sub O, is called the intercept A. And we'll see what the intercept A really is all about. Has to do with the difference. It's a small number typically. It's a few minutes of arc. And here's what that is all about. If we make an observation of the sun over its geographic position, as we will find out in the site reduction, we'll find out how we do that. We'll get a calculated altitude. Here's H sub C, you see it right here. Here we're using an assumed position, not a dead reckoning position. We'll come talk about that in a moment. If we then have compared that H sub C with H sub O, and if H sub O is a greater altitude, you can see graphically, we're not here, we're here. And the difference between those two is called the intercept A. And we can then plot that result by plotting a line of position at that point, a few miles from the assumed position. Conversely, if we observe an altitude that's smaller, then we're further away from the AP, and our intercept A will be away, and I have a line of position there. Line of position is just a small element of a circle of position. We'll be dealing with such a small area that we can approximate it by a straight line. So that's what we talk about H sub O and H sub C. And in order to do this process, this site reduction process, requires a solution of a triangle geometry, and we'll go into that. And please don't leave me while we do this, because we don't have to understand all these things, but I feel obliged to share them with you. So in plane geometry, if there are two sides of an included angle of a triangle, like that, then you can measure or calculate. Certainly you can measure this distance right here, and you can measure the angles in here. In plane on a piece of paper, you can do it with a tape measure. And you can measure the angle with a protractor. However, you can also do it with trigonometry. And here, I hope you don't leave me, because you don't have to remember this trigonometry. But recognize you can either measure it, if it's a small enough triangle, or you can calculate it. And if you wanted to calculate that, here are the formulas for that. That's, you can calculate for the side C, this side right here. And you can follow this formula to calculate the angle B. So that's all plain fact. You don't have to remember the trigonometry. I'm just saying there are ways to do it, either by measurement or by calculation. And that's true of triangles. If you know two sides in an angle, you can do the rest of the sides. The same is true for us on Earth for the navigational triangle. We actually have a triangle. We can create a triangle from our assumed position or our dead reckoning position, and the geographic position of the body, which we have gotten out of the almanac, and the elevated pole. And those three things, points with the sides between them, make a triangle. And we can use triangles solutions in the same way we did for the plane triangle. Notice the sides are not linear, they're angles, so we can calculate. And here, don't have to write this down. For the calculated altitude h sub c, you do that trigonometric calculation. You can find these two formulas in any book on navigation that you look for. However, like I said, don't despair, because there are tabular methods that you can use where you look up various numbers and only do addition and subtraction to come up to find h sub c and to come up with z. So let's think about this triangle for just a minute. Here's our navigational triangle. Let's see what we know in this triangle. Here's the assumed position and has a latitude, but by the same token, it has a co-latitude, 90 degrees minus latitude. So we know that side of the triangle. Same thing with the geographic position. It has a declination, which is the equivalent of latitude of the geographic position. And we can know what the co-declination is, which is 90 degrees minus the declination. And see where my little arrow is. There's a little arrow. So we know that side. And then we know what the difference between these two longitudes is. We call it the local hour angle. We measure it around in the opposite direction, or in not within the triangle, but outside of it. And that's called the local hour angle. So we know two sides and an angle, and we can do the same sort of computations. We can calculate the third side with a table or a calculator. And that's the radius of the circle of position, which I have not illustrated here. And we can solve for the azimuth angles too. So this is called site reduction. It's a solution of a spherical triangle rather than a plane triangle. And that's all you have to know right now. And don't remember the formulas. So first, we decide what position we're going to use for the reduction. We can use where we actually expect to be, think we are, or we can use a position close to that makes it convenient to use a tabular reduction. So dead reckoning is where we think we are. And assumed position is one we will assume that's nearby there, but we can assume a position that gets rid of extra minutes of arc. And it's for ease of reduction by the chosen method. Let's go through some of the chosen methods, or some of the methods we might use. Some methods use the dead reckoning position. Some reduction methods, tabular methods particularly, use assumed position. Very early on, up until about 1800, navigators had to learn how to use trigonometric log tables to do their site reductions. As a result, it took somebody who was fairly adept at understanding things and had a good memory for how to do the process, and a big sheet of paper to do the reductions. They started being skinnied down into smaller volumes. One of the early ones was HO208. This is hydrographic office. They're called something different now, but they're still 208. Use this in assumed position. Adjutant HO211, which actually was the method I was raised on when I was learning celestial navigation in the 1960s. DR, one of its real advantages, it used the DR position. Then the Navy came out with a 9-volume set so that you could do a tabular solution to the nearest 1/10 of a mile, because the Navy always wants to know where its battleships really were. So 1940s, another set of tables, 1950s, another set of tables. Notice 9 volumes. That HO214 had a stack that was about this high, of 9 volumes, which you had to have on your battleship bridge table, navigation table. The air methods, HO 249 is an air method that came out in the 1950s, only 3 volumes, but still cumbersome. All of these came out in their extreme volumes because computers didn't exist before 1960. So you had a tabular method. You could look it up, you could do the trig laboriously if you learned how to follow all the formulas, or you could use one of these tabular methods, and that was fine. But this all was before computers were available. That's why they existed. So nowadays we have 2 things which we use. One is the Nautical Almanac site reduction tables. Since the 1990s, those tables are 30 pages of tables. They're bound into every issue of the Nautical Almanac. Straightforward to use. Lookup methods, no trig, just look up and do additions and subtractions. The other is to go through those brutal formulas with a law of cosines with a pocket calculator, hopefully one that's programmed to already do the thing for you, so you only have to enter the entry levels. So we're going to use those. So let's use a tabular method, use the Nautical Almanac method. As I said, there are 30 pages bound into the back of every Nautical Almanac. The tables are same for every year. So you can use the tables from a 15-year-old almanac because they're precisely the same tables. And we use a standard reduction form. Notice this says Nautical Almanac site reduction table. And here are the places where we fill things in. And when we're all done, we come into the end of this with a computed altitude here and an intercept A there and a ZN and azimuth. So all this is just look up tables and 3 page openings to look up these numbers. And then you should do some addition and subtraction, and presto, you come up with a computed altitude. And as we've just found out, when you combine that with the observed altitude, the difference yields the intercept A. So you do the same thing with sines and cosines. Here is a site reduction table by the law of cosines. And here, right here, you see those painful formula. But you can punch those into a hand calculator, scientific calculator. You need one because it has to have transcendental, what's called a transcendental functions, which means it has sines, cosines, and tangents, and the converse of those as well. But the result is the same. You have many button pushes, or in my case, I have this 42S. I can call it up on my computer and it's programmed to do the solution. I don't have to punch in all these numbers. I just punch in the entry levels, these ones right here. And when you're done, you come up with a computed altitude and intercept and the direction. So given the computed altitude and we combine it with the observed altitude, we get the intercept. And now we have to plot that thing, plot the results. So let's go ahead and do that. Here's a chart of the North Atlantic. Not very useful to the navigator, except occasionally a navigator will plot his midday position on that chart as he proceeds across the ocean. If we want to do a course from Portsmouth, New Hampshire, and see if I can make this go. There it goes. I should make that a darker line. I'll do that. So go down south of the Grand Banks and then straight across on a run line course. And, but I'd say, and possibly small scale to keep track of daily progress or even hourly progress. So what we, because here's 300 nautical miles, so you can see the impossibility of trying to plot something to a mile or two. So we use a large scale plotting sheet in our small vessel or even reasonable sized vessel to keep track. Remember, we're pencil and paper people now. Don't have a computer. So we have the almanac and the site reduction tables, and then we will have miniature plotting sheets of about this size. And it's called a VPOS plotting sheet. Here's a copy of it. It's available from any government or navigational supply dealer. And it is built, it's available in tablets of 50 sheets, printed on both sides. If you were a sailor, you'd probably buy a couple tablets of that, and that should be enough to get you across the ocean. And they can be filled in to represent a specific latitude and a chosen center longitude. Notice the latitude parallels are pre-printed. And here's 10 miles. 10 nautical miles. So we can work to a couple of nautical miles fairly easily with this. But we have to construct it to be at the latitude we are at. And the plotting sheet allows construction methods to make that very easy. We plotted in this meridian of longitude and the second meridian of longitude using a scale on the outside. I won't go into how you do that. And then we can, down at the bottom, we can draw a line across this graphic at the appropriate latitude. And that scale, turns out, should be the same as the scale. And we can check that. So how does the ship's dead reckoning relate? Let's put a track on this. We're plotting, this is not across the ocean now, this is a different place. If you're a navigator, you will put a dead reckoning plot and give a speed, a course and a speed, in this case 120 degrees, true direction, and a speed of 20 knots. This is a power vessel, of course. And we can put in dead reckoning positions, speed 20 knots. So we, from here to there is 20 nautical miles. So that's that same distance right there. And let's say at 10:33, we have plot our position at 10:33 and we take a sun sight. And we've used the nautical almanac site reduction method. We're going to assume position. And we plot that 7 miles towards at 151 degrees, that's the azimuth. And then plot the LOP, line of position. That's part of a much larger circle of position, of course. So there's our sun line. And you say, what use is that? Well, it probably isn't too much use, although it gives you it'll give you some indication as to whether you're making more progress than your 20 knots or less progress. It looks like it's ahead of you right here. That's the near the estimated position. So now this one's screwed up. So something in this plot has just changed. So notice my meridians of longitude jumped over, and I'm going to have to go correct that the next time I present this. So let's say at 10:33, you also take another site. Let's say you take a site of the moon. And because those are about the same time, 10:33, 10:44, you're going to be where they cross. not up here, but down here. And that's called a fix. And we label it, and we continue our plot, not from where we thought we were, but from where we really were, and continue on our way. So that's the process of observing a site, reducing a site, and plotting a site. So let's take a deep breath here and say, why was that fix 16 miles from where we thought we were? So a prudent navigator would start pondering that about what was the last fix? When was it? Is there current running that we're unaware of? How about leeway? Or how about steering error? How about site reduction error? How about plotting error? And then apply that knowledge in developing a new DR projection. As an ancient navigators would say, a navigator should practice constant vigilance. There is a common practice to deal with that, observing only the sun, and that is to do running fixes during the course of the day. And here's a quick example of a set of running fixes. Often a morning sight as we're proceeding along. Here at 0834, we got an observation of the sun. Later in midday, we took another sight of the sun. Notice here it's the sun is in this view is in the east. There's a little observation away. Here the sun was south, more or less south of us, a little east of south, but not much. And then we can then advance the earlier sight by the vessel's advance. And we'll label it, as we've done here, the earlier sight advanced to the later time. And where they cross is a pretty good guess of where we might be. And that's called a running fix because the times are a couple of hours different. So we don't know quite what's happening with us in the meantime. That's called a running fix. And people on crossing the ocean very often use just the sun and use running fixes during the course of the day to keep track of where they are. So we haven't talked about the small stuff, and I'll identify some of the small stuff. Multiple steps in site processing and a lot of minutia. The corrections for the raw sextant readings, the taking out of the nautical almanac's data, which is a lot of little bits and pieces have to be added and subtracted, taken into account. The performance of the site reduction process itself, which we have seen on those forms, might be relatively straightforward, but you might have made an error of adding something rather than subtracting something. And that's all these things I'm mentioning: entering the tables, filling out the forms, interpolations, algebraic signs, summations, and then the care in preparing the plotting sheets. So a lot of small stuff that we would have to learn a lot more about. But I want to say that that's what takes the time in a course on celestial navigation, and why we spend hours and hours, not just 45 minutes. Review of the key concepts. An individual site yields a single line of position. That line of position is a function of the sextant observation alone. Remember, we can reduce a site, but we can't plot for an LOP without an observed altitude. And the dead reckoning position or the assumed positions serve only as a reference points for the site reduction and plotting. Bottom line, one site yields a single line of position. Two independent sites in close sequence yield a fix. And the crossing of those two lines of position on a chart will give you a latitude and a longitude, which you will log, because you should keep track of what your latitude and longitude are as you proceed across this blue ocean. Then you know where you are. In GPS applications now, and we'll talk about them just very briefly. GPS technology involves a constellation of as many as 20 satellites circling the Earth at all times. And they carry with them a precise time, and they will find out where you are on your road mapper or on your marine chart plotter, and will tell you where on those two things you are. Those GPSs will continuously provide an exact latitude and longitude. And although those will be transparent to you as a user, it will tell you where on these two things you really are. You're right there and you're right here. And if you dig deep enough into the menu system, you can find the exact latitudes and longitudes, but you may have to dig pretty deep on your GPS system. So let's review the steps as the last step, and then we'll be finished. Keeping up with the dead reckoning plot, that's what you should do all the time. So you know where you are at any given time, or your best guess of where you might be. So that when you have a disaster and you want to talk with the Coast Guard, they say, what is your position? You should be able to answer that question. So we take a site, record the time, we look up the almanac data, we reduce the site, we plot the resulting line of position, or plural lines of position. And that's the essence of celestial navigation at sea in 45 minutes. I hope we didn't lose you along the way, and don't pay much attention to the trigonometry. I had to put it in there because I felt obliged, but we can do it all with lookup tables without even looking at a sine or a cosine or a tangent. With some training in the minutia and further practice, you can all do it. All, I hope, 25 of you who might be looking at it this time. So there we go, and we'll open it up for questions at this time. And I see there are a couple of things in the chats.
Mm-hmm.
And
yeah, so I want to invite anyone to add any questions that they might have for Nate. I have a couple to start us off while we're waiting. So you made the comment about a good navigator would say, why is there a 16-mile difference between where we thought we were and where we actually are? So how close, I mean, at what point is it like, okay, that's close enough? Or is it always we need to be, I mean, is there any wiggle room there, or?
Of course there is. It depends on how careful a navigator you are and what kind of waters you're sailing.
Mm-hmm.
A careful navigator would like to, with the dead reckoning plotting, like to know where his position within a couple of miles. That's a good thing to do.
Okay.
So that when an incoming vessel starts approaching you, you can say, I know where I am. This is where I am. Stay away from me. If you lackadaisical in your navigation, it might be that your actual position might vary from your dead reckoning position by a dozen miles, maybe 2 dozen miles. And you can slap the back of your hand and say, I'm not going to do that again. Yeah. So there's no direct answer to your question.
Okay. Okay. And then I had another question. So you mentioned that the sun can be helpful as an object to pay attention to, just because it's in the sky for so much during the day. But
day.
then you mentioned stars as well, planets, the moon. So during nighttime, is it just whatever is it most easily visible, or is there a celestial body that is kind of the go-to for most people?
No, is the answer at night.
Okay.
So among navigators, the sun is available every day except for
Mhm.
clouds. All day, all solar day. The planets and the stars are really only available after civil twilight for about 45 minutes.
Yeah.
That's both in the evening and the morning and the evening. And that also presumes that there are no clouds.
Right.
And so what happens after the end of what's called nautical twilight, which is as it gets darker and darker, the horizon disappears. And you can no longer make a reasonable observation during the course of the night because there's no visible horizon.
Mhm.
So although as we become students in celestial navigation, we learn how to take sights of planets and the stars. That's a great thing, and navigators will do that. But the average amateur navigator will fix on the sun. That's
Mhm.
what the best thing is. And what I was going to say, the moon we haven't talked about. The moon is available in daytime hours, but for about half the days of the month.
Right.
And with any luck, you can take sights of the moon because the horizon's there and the moon's there, and for 2 weeks out of the month, but the other 2 weeks you can't. So,
Right.
so the moon's a useful adjunct.
At times. Right. Right. Depending on where it is in its phases and those kinds of things. So if there is a really cloudy day, or is, let's say, a set of cloudy days, do you navigators have any tricks for something like that? Or is it just kind of like, well, we do the best we can and then wait for the sun to show up again?
The latter.
Yeah.
Yeah. And that's a real problem. If you
Mhm.
have 3 days of storm, navigators lose track of where they are. That's the reality. And they hope for the next glimpse. As that first Winslow Homer picture shows, it was a rather
Mhm.
cloudy sky, as you saw, except there was some crack visible through the cracks in the clouds. And that's what you hope for.
Mhm.
And if you can't get a noon sight, you take an afternoon sight, that's fine. Or you just cross your fingers. But, the real problem is not so much in blue water navigation as much as approaching landfall.
Mm.
And that's when you really have to start worrying about things.
Right. I'm thinking right now in the back of my head, I'm thinking about all of the um voyages that I've heard of from like the 1600s, the 1700s, and the 1800s, where maybe they were crossing the Atlantic and they were aiming for one location, but they ended up in a different location. And thinking about all of the information that they would have needed in order to get to that original spot, but depending on the weather or whatever else,
Well,
it just may have not
there
been
was a
available.
there was a methodology used for hundreds of years by navigators who didn't have accurate time,
Mhm.
who because the knowledge of the latitude of ports was well known, because you can observe the noonday sun from the port and know what its latitude is, and those latitudes were tabulated. So if you were approaching, and I have looked at the log of John Paul Jones, for example, when he went over to France the first time. That was not the first time for him, but it was the first time when he was in a colonial naval vessel. And that log shows doing just about what I'm described to you. As you come within a few days of what might be landfall, you gradually go up to a latitude that you know is the latitude of your destination.
Mhm.
And then you sail either east or west, depending on which way you're going, until you come to the landfall.
Mhm.
And that's what he did. It was very clear that he got to the latitude of Nantes, the mouth of the Loire, 3 days before he actually saw land. And then he stopped on day -2 and took soundings, and he couldn't reach the bottom. The next day he hove to and dropped the deep sea lead and found bottom at 80 fathoms. And he knew he was up on the continental shelf off France. And
Mhm.
then he was beginning to see shorebirds, and he began to see vegetation in the water.
Mhm.
And then he gradually worked his way in at the proper latitude, because he was there at the proper latitude, taking soundings as he went until he got close to the mouth of the river. And he had been to Nantes before, so he knew what he was looking for.
Right. Which I'm sure was
But
helpful.
there's no question, but people who don't spend much attention at that, and before the days of accurate time and almanacs, that many ships didn't make it.
Right.
First, maybe they didn't know what the latitude of their destination was, or maybe it's not north-south shore, but an east-west shore, which is not as easy to
Hmm.
fathom.
Right. Right.
Yeah.
Gotcha. We have another question that came through. Does the captain know how to navigate, or does he trust the navigator? So I guess that question is kind of, how specialized is that set of skills that the navigator has, or do others on the ship, including the captain,
Well,
know how to do this too?
I would say that anybody who achieves captain status has done this enough, so he is very skilled at it to begin with.
Mhm.
Typically, the navigational processes are delegated to the mates, first mate, second mate, third mate. And because the captain has lots of other things on his mind. And but that's what it is. And so there are navigators who do that because the captain, the first mate, may have a lot of other things on his mind as well. And so a skilled navigator, which is a level below those
Okay.
in terms of licensing and education, will be doing the navigation.
Gotcha. But with the idea that anyone above that position, for example, would be able to step in if the navigator
If
got
they haven't
sick
gotten
or
rusty yet.
something, or there was a problem.
If they haven't gotten rusty, yes. Mhm.
Excellent. Okay. I don't know if there are any other questions from people, but thank you so much, Nate, for taking the time to talk about this. I feel like I had a basic conceptual understanding of, you definitely use the sun and the stars, but I didn't quite know about all of the pieces of and how you bring the information together. So that was fantastic. For all of you who joined us, you will be getting an email tomorrow thanking you, asking for any comments or suggestions. So if you happen to have comments for Nate, questions for Nate, or anything like that, he's giving you his email here, but my email is also in the message you'll get tomorrow. So anything that you send to me, I will pass along to him as well, in case there are things that you think about after this that you are wondering about. And as I said, we'll post the link to the recording as well on our website and on our blog page, so that if there are things that you are wondering about again, or somebody else is curious about it, you can always find that link and watch that as well. So Nate, thank you so much. This was great.
You're welcome. And let me just take a moment. As
Absolutely.
you know, I'm in the middle of teaching a celestial navigation course for the Power Squadron, which we had to terminate or suspend in March 2020. And we're about ready to pick that back up again and see how many students we can pick up. And one of the students may well be still listening in, Lisa Marshy, which was, as I told you, in a catamaran down in the Berry Islands, Bahamas right now. And if you're still listening, Lisa and Dave, I hope you found this interesting.
This was great. Thank you. And I want to Thank everyone for joining us. At the moment, we're going to keep doing this in a virtual form at least for another month or two and kind of see how things are going. And then possibly when we restart in person, we'll keep a virtual option open for those of you who are farther away. I also just want to put in a quick plug for those of you who are in the Central New Hampshire area. We are doing our Aerospace Fest at the McAuliffe-Shepard Discovery Center in person again this year. It is Saturday, September 4th. It will all be outside except for the planetarium shows themselves. So if you're in the area and we're hoping for really good weather, please come by because we'll have all sorts of STEM activities, opportunities to learn about astronomy, engineering, even some artwork as well. And we hope to see you there. In the meantime, if you have any questions or comments, please send them to me. And when we have our next Superstellar Friday all set up, I will send out that information to everyone as well too. Thank you. I'm going to end it because it's always a little weird to figure out exactly when the end of the meeting is. So I will make that decision. Good night, everyone. I hope to see you in person soon.